properly derate conductors in an underground duct system, especially with multiple circuits, you need to follow a series of steps based on the National Electrical Code (NEC). Firstly, determine the total load. Calculate the total amount of current in amps that will be carried by all of the circuits within the duct system. This involves summing the loads of each individual circuit. Secondly, calculate the total number of conductors. This requires determining how many parallel conductors exist for each circuit within the duct bank. Add up the number of conductors from each circuit to get the total number of conductors in the system. Thirdly, determine the duct area. Estimate the cross-sectional area of the duct bank. This might involve measuring the dimensions of the duct bank and calculating the area based on its shape. Fourthly, calculate the current density. To do this, divide the total load, which you calculated in step 1, by the total number of conductors, which you calculated in step 2. This will give you the current per conductor. Next, divide the current per conductor by the duct area, which you found in step 3, to determine the current density within the duct bank. Fifthly, determine the derating factor. The National Electrical Code (NEC) provides tables that specify derating factors based on the number of conductors in a raceway or duct bank. Specifically, refer to Table 310.15b2 of the NEC. This table provides ampacity adjustment factors for more than 3 current carrying conductors in a raceway or cable. Locate the appropriate derating factor based on the number of ducts and the number of circuits within your duct system. Sixthly, derate the conductor ampacity. Multiply the ampacity of each conductor, as determined by its size and insulation type, by the derating factor you identified in step 5. This will give you the derated ampacity, which is the maximum current the conductor can safely carry in the specific conditions of your duct system. The formula for derating ampacity is derated ampacity equals ampacity of conductor multiplied by derating factor. Let's go through an example. Suppose the total load is 600 amps. There are 4 circuits. There are 3 conductors per circuit, giving you a total of 12 conductors. The duct area is 0.5 square feet, and the derating factor from table 310.15b2 for 24 ducts with 4 circuits is 0.8. Then, the current per conductor would be 600 amps divided by 12, which equals 50 amps. The current density would be 50 amps divided by 0.5 square feet, which equals 100 amps per square foot. And finally, the derated ampacity would be 50 amps times 0.8, which equals 40 amps. In this example, the conductor ampacity would be derated from 50 amps to 40 amps to ensure safe operation within the duct system. The NEC provides guidance for derating conductors in various conditions. Several factors need to be considered, including ambient temperature, a number of current carrying conductors in a raceway or cable, and the presence of harmonics. For underground installations, thermal resistance of the soil is another important consideration. The ampacity tables provided in the NEC, such as Table 310.16 and Table 310.17, provide the allowable ampacities of insulated conductors rated up to 2000 volts. These tables are based on specific conditions, such as an ambient temperature of 30 degrees Celsius, which is 86 degrees Fahrenheit, and no more than 3 current carrying conductors in a raceway or cable. When these conditions are not met, the ampacity of the conductors must be adjusted using correction factors and derating factors. Correction factors are applied to account for ambient temperatures that are higher or lower than the base temperature of 30 degrees Celsius. These factors are found in the ampacity tables themselves. Derating factors are applied when there are more than 3 current carrying conductors in a raceway or cable. These factors are found in Table 310.15b2. The goal of derating is to ensure that the conductors do not overheat, which can damage the insulation and potentially lead to a fire. Overheating occurs when the heat generated by the current flowing through the conductor exceeds the rate at which the heat can be dissipated into the surrounding environment. In underground duct systems, the heat dissipation is affected by several factors, including the thermal resistance of the soil, the spacing between the ducts, and the number of conductors in each duct. The NEC provides guidelines for derating conductors and underground installations to account for these factors. The thermal resistance of the soil is a measure of how well the soil conducts heat. Soils with high thermal resistance will impede the flow of heat away from the conductors, leading to higher conductor temperatures. The NEC provides tables that list the typical thermal resistance values for different types of soil. When the thermal resistance of the soil is higher than the value used in the ampacity tables, the ampacity of the conductors must be derated. The spacing between the ducts also affects the heat dissipation. When ducts are closely spaced, the heat from one conductor can affect the temperature of adjacent conductors. This can lead to higher conductor temperatures and require further derating. The NEC provides guidelines for the minimum spacing between ducts to minimize this effect. The number of conductors in each duct also affects the heat dissipation. When there are multiple conductors in a duct, the heat from each conductor can contribute to the overall temperature of the duct. This can lead to higher conductor temperatures and require further derating. The NEC provides derating factors for different numbers of conductors in a duct. In addition to these factors, the presence of harmonics can also affect the ampacity of conductors. Harmonics are currents and voltages that are multiples of the fundamental frequency, typically 60 Hz in the United States. Harmonics can cause increased heating in conductors, transformers, and other electrical equipment. When harmonics are present, the ampacity of the conductors must be derated to account for the increased heating. The NEC provides guidelines for derating conductors in the presence of harmonics. It is important to note that derating factors are cumulative. This means that if multiple derating factors apply, they must be multiplied together to determine the overall derating factor. For example, if a conductor is subject to a derating factor for ambient temperature and a derating factor for the number of conductors in a raceway, both factors must be multiplied together. Proper derating of conductors is essential for ensuring the safety and reliability of electrical systems. Failure to derate conductors properly can lead to overheating, insulation damage, and potentially fires. It is important to consult the NEC and other applicable codes and standards when designing and installing electrical systems to ensure that conductors are properly derated. In addition to the NEC, there are other resources available to help with conductor derating. These include engineering handbooks, software tools, and training courses. These resources can provide more detailed information and guidance on how to derate conductors in specific situations. Some jurisdictions may also have local amendments to the NEC that must be followed. It is important to be aware of these local requirements and to comply with them. Conductor derating is a complex topic, but it is essential for ensuring the safety and reliability of electrical systems. By following the guidelines in the NEC and other applicable codes and standards, you can ensure that conductors are properly derated and that electrical systems operate safely and efficiently. Remember that the specific derating requirements will vary depending on the specific conditions of the installation. It is always best to consult with a qualified electrical engineer or electrician to ensure that conductors are properly derated. Always prioritize safety when working with electrical systems. Ensure that you are properly trained and qualified before working on electrical equipment. Always disconnect power before working on electrical circuits. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow all applicable safety codes and standards. If you are unsure about any aspect of electrical work, consult with a qualified professional. To summarize, derating conductors and underground duct systems requires a systematic approach involving several key steps. Firstly, accurately determine the total load that all circuits within the duct system will carry. This is the foundation for all subsequent calculations. Secondly, meticulously count the total number of conductors present within the duct system, accounting for parallel conductors in each circuit. This number is critical for calculating current density. Thirdly, carefully estimate the cross-sectional area of the duct system. This measurement is used to determine how densely the current is packed within the ducts. Fourthly, calculate the current density by dividing the total load by the total number of conductors and then dividing that result by the duct area. This value indicates the amount of current flowing per unit area. Fifthly, consult Table 310.15b2 of the National Electrical Code, NEC, to find the appropriate derating factor based on the number of ducts and circuits. This table is the authoritative source for derating factors. Sixthly, apply the derating factor by multiplying the conductor's original ampacity by the derating factor. This results in the derated ampacity, which is the adjusted maximum current the conductor can safely handle under the given conditions. Remembering and utilizing the formula derated ampacity equals the original ampacity of the conductor multiplied by the derating factor will result in the correct and safe handling of electrical systems.